Thanks, everyone. Today I'm talking about the joint work done with Luke, who is the architect behind all this, and myself, Twilling, software Schmidt Scholar, software engineer, help us build all of the systems, and in particular, Christine, who's very much a co-author, because she's down there in the basement with us, pulling wires, climbing ladders, drilling holes with us. So very much thanks, Christine, for that as well. But first, a fun slide. This is who I am. And me, the baby of the family, the youngest so far. And all of you, I know you guys are all judging like, ooh, he's going to carry the torch now, huh? Right? So that's me. But anyways, most of you are not stranger to this slide, right? That's the power grid, distribution grid of the past. In the future, we'll have more uncertainty, instability, bidirectional power flow, distributed energy resources, and all kinds of issues and challenges and opportunities introduced by renewables, right? So the question we try to answer today is, how do we build the next generation sensing and metering infrastructure to support the next generation grid operation, where we're pushing the grid closer and closer to the limit, right? So that requires synchronized metering, that requires high resolution, that requires real time. So we're answering that fundamental infrastructure piece that we believe that a lot of people are overlooking right now. So it's really, how do we probe the system and sense it to support grid operation? So this is our high-level philosophy, right? In the bottom, we have heterogeneous infrastructure from IBRs, right, EVs, batteries, to different metering solutions, to synchronous generators, the traditional generators, to all kinds of smart devices and legacy grid components. On top, we have a variety of applications that need to be enabled for us to achieve net zero emission, reliability, resilience, right? And in the middle, that requires a very robust linking layer. So that requires very good data, very good models, and flexible algorithms to achieve those goals and connect the infrastructure to the applications. And this theme has surfaced a few times over the past day and today as well, right? And this is an analogy in the internet where we have all kinds of different devices, from PCs, cell phones, to printers, to, right? In the middle, we have very robust protocols that connects those devices to a variety of very successful applications that are lucrative. So this level of scalability must be replicated in the power grid, and in our investigation in the distribution grid, for us to achieve our very aggressive climate goals and still have the grid being affordable and reliable. Okay? So our work focused on the middle layer. So a lot of smart people are working on this, working on that, working on algorithms, but not very many smart people or dedicated people are looking at the data piece. So that's what we try to tackle. And one final note on today's very short, 15 minutes, is we're trying to present not just what we did, but a framework approach on how to approach these type of problems. And for some of the algorithms and modeling that we did, we won't go into too much math details, but the idea is to show you what can be done and to spark some ideas, okay? So the first is the data piece. So we'll first contrast our approach with the existing metering approaches. On top right, we have this transmission network, the bulk electricity network, and there are PMUs in there, so phasor measurement units. These are very expensive, synchronized measuring units, very sparsely deployed, only 2,500 deployed in 2019. So that's the transmission grid, right, high voltage. In the distribution grid, over here, the traditional utilities approach is to use SCADA or ADMS, measure, again, very sparsely at the medium voltage level at the substation transformer sitting in between the bulk power system and the distribution grid. Or there's the bottom-up approach, right, in AMI, where the meters are measuring the customer panels at the households. And the issue here is you have so many households, it's very difficult to have enough coverage at all points of your network, right? So in practice, these systems are almost always plagued with data quality issues, synchronization issues, availability issues. So not a very friendly system to work with as well in practice. And here's our approach. We want to meter at the distribution transformer level, and there's several benefits to this, right? You have this tree structure, so you're not metering as many nodes compared to AMI. You're also working with a low voltage system, so that makes the installation much easier and lower cost, right? And in our approach, our data is synchronized. We'll have phasor and waveform. And we'll have this additional privacy-preserving structure because we're aggregating 10, 12 households together. Right. So that's some real proof that we actually went in and did the work. So far, we have 37 meters installed. And that's kind of electrotopology and coverage. And that's some of the physical hardware that we put into the switchgear in our collaborating campuses, our collaborating utilities around the Caltech region. And here's the actual data set. There are 3 pieces to it. First is a synchronized waveform, right? At all nodes in the network, we have a common time reference because all of our meters are synchronized to the GPS. So we can capture waveforms together and align them to a common time reference. And that's available for our 37 meters and the 6 channels, 3-phase voltage and currents. From the synchro waveform data sets, and if we make the steady state assumption, then we can derive the synchro phasors, right? So that's the phasor representation of the waveform. We have that, in addition to the 37 nodes that we measure, we have that available for all of the network because of the third piece. We have the digitized network topology. So we have full visibility of the system. We can solve for the state, the entire state of the system, and get all of the branch currents and all of the nodal voltages. So our system, where we choose to meter, is fully visible. And that, again, that goes back to the approach, right? Where we can densely meter this layer so that we can run the state estimation. So I believe it's a very smart way to do this without breaking a wallet, but still have that level of visibility of the system, synchronized and dense. Okay. And we've built a variety of dashboards for our collaborating utilities and campuses, just on the practical side. So that's the data layer. From those time series data, right, the next natural question to ask is how can we build robust models to model the grids that we are trying to measure, right? And what I'm about to present is only one piece of the puzzle, kind of solves one problem in one particular approach. There are many other approaches one can take, right? So this is just one problem. So the problem is formulated as the following. Given a grid that you cannot really observe, right? Maybe you have partial information, and you meter a subset of the nodes in this grid. And the question is, how do you recover the original network topology, right? Then this is very important because the distribution grid, often you have breaker status that are undetermined. Your equipment can fail. Your transformer can degrade over time. And you would like to keep track of the topology and parameter changes so you can run your state estimator, you can run your capacity analysis, you can monitor your equipment and detect failures. So it's a very crucial piece of technology that's needed for grid operation. The algorithm is 2 pieces. The first piece is to identify the Cron-reduced network, which is the effective admittance between all of the nodes that you can observe, right? So from this reduced graph, the next step is how do we map this reduced graph into the original graph where you do have hidden nodes where you do not observe. Right? So a two-piece puzzle here. The first one turns out to be relatively simple if you can measure densely. It's really just a linear regression problem subject to convex and linear constraints. There's some subtleties in dealing with real data, but that's in the details. Now you have the Y bar, so that's the Cron-reduced admittance matrix. You can run Stevens' algorithm to do this reverse Cron reduction in the second step, where we identify the maximal cliques, separate the maximal cliques, and then in each maximal clique, you do this identification and reintroduce the hidden nodes, and at the end, you put it back together. So that's a high-level overview of that algorithm. And if you are interested in more details, Steven has written 40 pages for you, available on archive for that. So just take my word for it. It works. You can recover the topology if you meter in the same approach that we do. Right. OK, now you have the 2 fundamental pieces, the time series and the topology, the whole network. To me, I believe the most important application you can run is state estimation, where you solve for all of the currents and the voltages across your network. Right? So given these 2 pieces, this problem, again, becomes fairly simple mathematically. And again, in implementation, there are subtleties to improve the accuracy and robustness, but really it's just a linear regression problem subject to a linear constraint, where the Y matrix we have just recovered from the previous step, right? And the I and the V are the ones we measure, and we want to recover all of the I's and the V's in the network. And we've done that for the network that where we deployed our meters. So this is a subset of that network where we can solve, as you can see, the branch currents and the nodal voltages. And we've built a variety of visualization apps thanks to Tuiling's efforts on those systems. So this is my last slide. State estimation is really a very powerful tool. You can run capacity analysis, just enables, or you can monitor your equipment, the overall lifetime aging of a particular transformer. It all depends on the current you put through it, right? Another exciting application of that is once you have your full state, you can solve in real time, densely, the carbon intensity at all points in your network, right? So you can solve for the carbon intensity down to the circuit breaker, down to the line, down to every single node. So that's also something we did just to illustrate the power of state estimation. Okay, so hopefully today I've introduced to you not just the work we've done, but a new way of thinking about measuring and sensing to support the next generation grid applications. So thank you, and now I'll welcome some questions.
Any questions? What do you mean by carbon? Like, what is it? How do I interpret nodal carbon intensity?
Sure. Nodal is a little bit less intuitive. So let's start with branch. So branch is just how many grams of CO2 per kilowatt, right? You're pulling. So for PV, it's 0. For fuel cell, it's something low. For coal, it's something high. At a node, when you have multiple branches flowing into a node, it's a non-trivial thing to kind of account for how you calculate, right? So one approach is to say everything that flows into a node is homogenized. It's mixed together, just like water. That's one approach. Whether it's the right approach, it's debatable, but that's an open question. But the idea is kind of this kind of a water or liquid flow. But exactly how you account for it, that's a really good question. And there's no market, and there's currently no need for such a debate. But I think intellectually it's an interesting thing to think about. Whether you think about it as a homogenized mix at a node, it's well mixed, or it's something else.